When ester enolates react with esters, the reaction is a condensation because one molecule of an alcohol is displaced. When ketone or aldehyde enolates react with ketones or aldehydes, the reaction is an addition because after protonation, the molecule of the aldehyde or ketone is added across the carbonyl group. Those addition reactions are called Aldol condensations and are the subject of this video. The first step in understanding aldol condensations is to recognize that carbonyl groups are intrinsically electrophilic and enolates are nucleophilic. The next step is to understand the pKas. So for instance, an aldehyde is better able to support a negative charge as the aldehyde enolate than an amide, because amides are less acidic than aldehydes are. These effects are cumulative. If there are two electron withdrawing groups on a methylene, that methylene is better able to support an enolate than just one electron withdrawing group. And if there's an especially good electron withdrawing group, like a nitro, then the methylene becomes relatively acidic. Simple examples of aldol reactions involve no relative stereochemistry. Only one chiral center is formed. In most cases, however, diastereoisomers result, where one is called syn and the other is called anti, based on their extended conformations. For intramolecular aldol reactions, sometimes it helps to number the carbons. So in this example, if the nucleophilic carbon of an enolate is C2 and it cyclizes onto the carbonyl at C6, then a 5-membered ring must be formed. Similarly, the carbon at C2 in an enolate must be 6 atoms away from the carbonyl to form a 6-membered ring. A 7-membered ring can be formed from a 1,8 dicarbonyl compound, and this 10-membered ring is formed from a 1,11 dicarbonyl. Incidentally, an easy way to draw 10-membered rings is to draw two 6-membered rings fused together, that is a decalin, then erase the bond between them. A similar strategy can be used for 14, 18, 22-membered rings, and so on. For some intramolecular aldol reactions, there are two possibilities, and since everything may be in equilibrium, both could be sampled. This 2,5-diketone can enolize at C3 to attack on the carbonyl 5, giving a cyclopropane. Kinetically, that might happen very fast, but thermodynamically, cyclization at C1 on carbonyl 5 is preferred to give a 5-membered ring. In this aromatic 2,5-diketone, there's really only one choice for enolization, and a 5-membered ring is formed inevitably. Many aldol products will dehydrate under the reaction conditions to form enone. This can be a useful reaction in cross-couplings between enolizable carbonyl compounds and non-enolizable ones. The enols produced are extremely useful. Cross-couplings between two different enolizable compounds of similar reactivity, however, are very hard to control. For example, this enolizable aldehyde may undergo homocoupling. It can be reacted cleanly with non-enolizable aldehydes, but a mixture of products would form if it were reacted with a similar enolizable aldehyde. Favored ring sizes can be used to control the products in these reactions. So only a 5-membered ring forms in this first reaction, and not a strained 7-membered ring. And a 5-membered ring is preferred by cyclization of C6 onto C2 than a 7-membered ring, which would be formed by cyclization of C1 onto C7. Similarly, in the very last example, only a 6-membered ring forms, and not the alternative 4-membered ring. Bye-bye.